Okay, here's our video for Chapter 2, Part 3. Let's see if I can get my PowerPoint cooperating here. Okay, so some basic inorganic chemistry review. Remember that inorganic chemistry generally means that things that don't contain carbon. So even though water is super important in life and participates with a lot of organic chemical reactions, water itself is an inorganic, no carbon. Likewise, oxygen, calcium phosphate, metal ions, these are all non-carbon containing inorganic compounds. Now, there are just a couple of exceptions. Carbon monoxide, carbon dioxide, and the bicarbonate ion are exceptions to this rule because they do contain carbon, but we still call them inorganic molecules. All of our organic chemistry has to do with these biochemicals, biologically active molecules or molecules that are made by living things. And that's what our next section is all about. Just a quick review so that you remember these vocabulary terms. I've bolded them so that they stand out. If you're not sure what they are, go ahead and make a flashcard. If you already know what they are and how they are related, then you don't have to worry about it. Let's see here. Concentration gradients, measure of the number of particles of a solute per volume of a solution, right? So the more concentrated something is, the more particles it has in the fluid that it's held within. And there are just a couple of terms. We'll use these and revisit these terms all throughout the semester. This is just an introduction, or maybe review if you remember osmolality. That's kind of a tongue twister. It is specific to this unit, right? Reflects the number of particles in 1 kilogram of water, osmolality. And so we'll see that later on when we're talking about concentration of sweat and urine, things like that. 1 osmol, which is where we get that term, is of course equal to Avogadro's number, 6.02 times 10 to the 23rd. Remember that? In 1 kilogram of water. Man, that Avogadro guy really figured out a lot, and of course gave us guacamole, which is great. Love it. Units used by physiologists are milliosmoles, because we don't want to talk about a whole kilogram of water. We want to talk about just a small concentration, a smaller amount. Concentrations of the body fluids influence the movement of fluid into and out of the cells. Of course, the best and easiest example to think about is edema. I don't know if you've ever worked with a patient who had a whole bunch of fluid in their tissues, right? Really swollen, puffy under the eyes, fat and swollen little sausage fingers. That's all related to what we're talking about right here. So it's very important you understand these definitions so that we can start to talk about how different hormones or different lifestyles affect our osmolality. Okay, acids and bases, salts and buffers. Hopefully this is all review for you. If you need to pause right here to sort of take in this slide, let me know. We'll talk a bit more about pH right here and kind of bounce back to the other slide. pH is, of course, a measure of acid, base, and relative acidity or alkalinity. So distilled water or neutral, pure water is at 7.0. Distilled water, pure water at neutral 7.0. Blood, look at this. On a 14-point logarithmic scale, our physiological range is 7.35 to 7.45. And I'm just going to add that to the slide right here, actually, while we talk about it. So the mean, of course, being 7.4. That's what you see in this slide, 7.4. But it's really sort of a dynamic range. If we're working out or we consume very alkaline foods, it might fluctuate a little bit, but we consider this the normal physiological range. So if we have very acidic things, they have a very low pH, which is high on this scale, but a low pH, 1, stomach acid, pH of 2.0, lemon juice, right? On the other end, baking soda is an alkaline thing, sodium bicarbonate, right? Soda ash you get out of a wood furnace, for example, oven cleaner in lye, sodium hydroxide, very, very high pH. That means basicity. You very rarely see that word. Usually we use the word alkalinity. So something with a high pH is not acidic. Something with a low pH is acidic. Something with a high pH is alkaline. Now, almost all of the chemistry that we talk about is in this very tiny, narrow range, because if our patients become acidotic, or if they have alkalosis, man, they get sick or die. So we don't ever see ranges outside of these things right here. What else do we need to know? Oh, in order for you to not die from alkalosis or acidosis, you have to have a buffer, right? A buffer is something that resists big swings in pH. And these are the most important biological buffers. Man, I don't like to edit while I'm presenting, but I'm going to do it anyway. Look at this bicarbonate. This is absolutely the most important biological buffer that we talk about in this class. HCO3 minus bicarbonate. Likewise, phosphates. Proteins can serve as buffers too. And there are things in our lungs and things in our kidneys that help to resist huge changes, huge swings in pH. Next, here on slide 42, oxygen and carbon dioxide. Do you know why these are important in human physiology? I'm sure you know that they are important, but do you know why? Oxygen is actually required for the final step in a series of reactions used to extract energy from food. So how interesting. You can starve yourself for 2 weeks and you won't die, but if you run out of oxygen, you'll die really quickly. Carbon dioxide is on the other side of that chemical equation. It is the product, the waste product of that energy extraction. And so we're going to talk tons and tons about oxygen and carbon dioxide. We'll close this video and we'll come back for chapter 2, part 4 momentarily.